All right, so this is Math 150. I believe this is lecture 15. And what I want to do today is I want to do one more lecture on applications. It will be a chance to see a little bit of multivariable calculus, but it's going to be a little bit more on applications of just one variable calculus and applications about trying to figure out how do you attack something mathematically. So I'm going to start with what should be an easy question, but it's going to be very hard to answer this in a mathematically precise manner. Can someone define dimension for me? So if you can't define something and you're using it, this is an issue. So can you give me a rigorous definition? And if not, can you at least give me a bunch of examples so that maybe I can isolate what the definition is from your examples? Can you give me examples of dimension? Yes. Okay, why the number of planes? So are you saying like a flat plane is a one-dimensional object? Two-dimensional. All right, so a plane is a two-dimensional object. So this piece of paper, the screen would be a two-dimensional object. Okay, so it's not a definition, but it's at least an example. Can somebody give me an example of a different dimensional space? I'm sorry, a box would be 3D. We've all missed something. If we go back a little bit, a line. All right, so we've got a line is one dimension, a plane is two dimensions. Yes. Good, so this is like a linear algebra definition. The number of independent directions we need so that everything can be written as a combination. So in the plane, there's more than one pair of directions I can choose. I can do the north and the east. I could do the northeast and the southwest. I could do the northeast and the east. I have lots of different choices, but no matter what choice I make, I always only need two directions to describe anything in the plane. So what do you notice about these numbers? 1, 2, 3. What kind of numbers are they? Integers. Be more specific. What kind of integers? Positive integers. So you could argue maybe a point is zero dimensional. Are we going to have a negative dimensional space? No, like if I give you the probability of winning, what can you tell me about the probability of winning? It's between 0 and 1. What percent effort can you give in a game? What's the maximum? Yeah, the abuser. They gave 120%. No, they didn't. They might have given 120% of what you thought they could give, but they're not able to give more than they can give. Your chance of winning is going to be between 0 and 1. So it seems like maybe dimensions are going to be these positive integers. So here is a nice rigorous mathematical definition of what we'll call the Hausdorff dimension. So we need the notion of dilating a set by a factor of r. And what that means is you take every point in your space and you multiply all of its coordinates by little r. And that would be called the dilation. So if I take a circle of radius 1 and I dilate it by r, I get a circle of radius r. And so we define the Hausdorff dimension as follows. So take some set S, and we'll assume it lives in an n-dimensional space. So Rn is n directions. Each one is going to be, real axis. So I look at all my points in S, x1 through xn. And then if I take every point in S and I multiply it by R, that's going to give me a new set. And what I'm going to do is I'm going to see how many copies of S do I get. So let's say I get C copies. So I'm going to then say my dimension D is the number such that R to the D equals C. Let's try to see if this makes sense and reduces to giving us the answer we know in some simple cases. So we had 3 suggestions. Which suggestion should we look at first in trying to understand this? Line, plane, or box? Which should we do first? Line. Let's start with the easiest. So if I give you a line from 0 to 1 and I triple it, I triple every point, what would I get now? 0 to 3. And so, the slow delay. Okay, so here's the line from 0 to 1. I triple it, I get the line from 0 to 3. I have 3 copies of my initial line segment. So if I try to solve the equation R to the D equals C, R equals 3, C equals 3, so D equals 1. So we've shown that if we define dimension as we did on the previous slide, we actually get the answer we would expect for the line. Building on the success of the line, what do we move on to next? Plane. So let's take a unit square. If we triple every point, how many squares would we get now? We start off with a unit square. So the sides, it was 1 by 1. Now what would it be? So what would we get now? 3 by 3. So how many copies of the unit square would we have in something that's 3 by 3? Why 2? Well, it's 2 axes, but how many copies of the initial square? We initially had a square that was 1 by 1. We would have 9. So if you look at the picture, I start off with a square that's 1 by 1, and I triple it. So I now have 3, I go 3 times farther in that direction, 3 times farther. In this one, the point over here at 1/3, 1/3 would expand out to the point 1, 1. The point at 2/3, 2/3 would expand out to the point 2, 2. So I now have 9 copies of my square. And so when I look at this, if I try to solve r to the d equals c, I get 3 to the d equals 9, and so we get 2. I'm assuming at this point, no one is going to be shocked if we do this for the box and we get the box as dimension 3. So I'm not going to bother doing the box. I'm going to instead turn to a more interesting set, the Cantor set. So the Cantor set is defined as a sequence of iterations, and this is what we're going to do. We start off with a unit interval 0, 1, and at every stage, we throw away the middle third. There's a tremendous amount you can say about the Cantor set. I'm only going to do the very little. So we throw away the initial third, and now we're left with something from 0 to 1/3 and 1/3, and 2/3 to 1. And then at each stage, we look at all the segments that are left, and we keep throwing away the middle third of what's left. So we would throw away from 1/9 to 2/9, and from 7/9 to 8/9. And so we can keep doing this a bunch of times. Initially, we have something of length 1. What's the length of the next level? 2/3, the next level. I'm sorry? We start off with 1. We kept 2/3 and we threw away 1/3. So we have 2/3. Every time we go to the next level, we throw away 1/3 of each segment that's left. So how much would the next level be? 1, 2/3, 4/9. We keep 2/3 every single time. So the next level would be 8/27, 1681. I'm scared to try to do multiplication higher than that, so I'll just say that the pattern hopefully is clear. What's the length going to go to as you go further and further down? 0. So this looks like it should be something that has dimension less than 1. If it had dimension of 1, this should be some kind of interval somewhere. This is something whose dimension is going to be less than 1. Its length is going to 0. But maybe its dimension is greater than 0. So what I want to do is I want to try to figure out what would be a good thing to dilate this by so that I get an integer number of copies of it. So remember, I'm throwing, this is after so many levels, I keep doing this infinitely often, and I have a very small collection of points left. It has 0 length, but it's still, if you know what uncountable sets are, it has a high level of infinity. Anybody want to guess what would be a good factor to dilate this by so we know how many copies we have, an integer number of copies? So is there anything I could multiply this by so that maybe this part over here would expand out and become a full copy of the whole set? It would be a good thing to multiply by. So give me some possible integers. 1 is not good. Let's just try all the integers. If we tried 2, well, this is going from 0 to 1/3. If I multiply by 2, I'm going from 0 to 2/3. That's not going to fit in nicely. What if I tried 3? Well, if I tried 3, then 0 to 1/3 expands out to 0 to 1. So this part over here would expand out and become the whole thing. This gap of length 1/3 would become a gap of length 1. Okay, well, still nothing there. And in this part, from 2/3 to 1 would expand out and become another copy, but now living from 2 to 3. So if I multiply, if I dilate by a factor of 3, how many copies do I get? I'm sorry, not 3. This part over here would expand out and give me a full copy. This is still empty. This part over here would give me a full copy. So how many copies would I have? 2. And so if I solve, I would get, how cuts it off? So if you look really closely, it says 3 to the d equals 2. And so you get about 0.63, which is the log of 2 base 3. It's not an integer, and it is between 0 and 1. So when I dilated by a factor of 3, I got 2 copies. Let's look at Pascal's triangle, which you've hopefully seen many times. I'm going to take every odd number and put a dot, and I'm going to delete every even number. And so this is what I would get if I looked at just the first 4 levels. If I looked at the first 8 levels, I would get the following. And I can keep looking at more and more levels. So if you want, you can watch videos of these later where it expands things out. I wrote this code years ago in Mathematica because I couldn't find anything that would just cleanly have them moving out. I've since fixed the code so that rather than going from left to right, it goes from up to down. It was just a little bit being lazy. Has anybody seen shapes like this before? So this is an example of what's called the Sierpinski fractal. It's a really interesting shape. And when you look at it, I'm adjusting it so that the number of rows is growing, but I'm always drawing it in the same box. Because if I keep drawing Pascal's triangle, if I keep adding more and more rows, well, it's just going off to infinity. I'm compressing Pascal's triangle down to always keep it inside a fixed box. And so what we can do is we can analyze this process. And what's really going on is equivalent to the following. Start off with an equilateral triangle, and let's throw away the middle. So we're going to split it into 4 smaller equilateral triangles, and we throw away the middle. Now we have 3 equilateral triangles, and for each one of them, we throw away the middle. And we keep doing it, we keep doing it, we keep doing it. That's essentially the same as what we're getting over here when we looked at Pascal's triangle, modulo just how things are being compressed and how it's being displayed. So let's try to figure out what the dimension of this is as we keep iterating this process. So we keep throwing away the middle equilateral triangle. This is a lot like the Cantor set. So again, right now, the whole purpose of today is just how do you think about mathematics? Can somebody give me an upper bound for the dimension of this? Doesn't matter if it's a good upper bound, just an upper bound that you are absolutely sure the dimension is not greater than this number. So, I'm sorry? So you would be willing to risk your life and the life of everyone in this classroom that the dimension is at most 1. Okay, so then that's not a good upper bound. I want an upper bound, yes. 4, absolutely, right? This lives in the plane, so 2 is probably safe. Well, maybe let's go up to 4 to be extremely safe. I would be willing to risk everyone's life on that one. Which reminds me, I do have to flip coins later today to see about the homework exemption. So I did bring some coins. Okay, so 4 is a definite safe upper bound. What about a lower bound for the dimension? And again, your lives might be at stake. Yes. 0, yeah. Let's be really safe. If my life is on the line, I'm going to say 0. I know, or might even say -1, but that's really bad. So 0 is a safe upper bound. Can you give me a little bit better lower bound that will actually work? 1, because if you think about it, we're never deleting anything on the edges. So they're always going to have a line. So it should be somewhere between 1 and 2. So 1 as an upper bound would be risky. 1 as a lower bound, I'm fine with. Let's try to calculate the dimension. Can you tell me what would be a good thing to multiply by so that this piece over here expands out and becomes the whole set and becomes a copy of the whole thing? What would be a good number to multiply by? So if I multiply by 4, this is going from 0 to 1/2. it's going to expand to 0 to 2. So just 2. So if I multiply by 2, this part over here going from 0 to 1/2 expands to be from 0 to 1. So this piece over here will give me a whole copy. So if I dilate by 2, how many copies of the initial set do I get? So this part over here would expand out and give me a full copy. This would give me a full copy. And the top would give me a full copy. So how many copies would I get? I would get, I think I heard someone say, but I couldn't quite tell. I would get 3 copies. So I would solve the equation r to the d equals c. So if r equals 2, c equals 3, then d is going to be the log of 3 base 2, about 1.58. And again, that fits with our intuition, greater than 1, less than 2. So there's lots of ways you can generalize. And this is one of the things you want to learn in whatever field you're studying. How can I push this further? Instead of coloring things black and white, I could actually do other colors. I could look at what is the remainder when I divide by 3. If the remainder is 1, I'll color it black. If the remainder is 2, I'll color it green. If the and so on and so on and so on. If the remainder is 0, I'll color it red. And you can ask about what kind of patterns would you get in situations like this. So I'll skip the rest. That takes a while to go through them. All right. So you should always be asking some questions. So a couple of years ago, I was teaching this in a senior seminar, and I asked, can you get any positive real number as a dimension? And one of my students was able to come up with a nice construction that, yes, you give me any number. If you love the square root of e divided by pi, we'll find a set that has that as its dimension. Okay. In the interest of time, I'm going to, I'll just very briefly say a little bit on the coastline paradox. That if you want to try to measure, for instance, what is the size of the British coast? Imagine, and this is a lot of work to imagine this, you have a 200-kilometer rod that you can somehow pick up and move around. And you use this to measure what's the coast of Britain. Well, you're obviously not going to be able to do a lot of fine work, coming in and out. And then you could say, well, let me do the best I can using that. And then let me do it again using a 100-kilometer rod. And then let me do it again using a 50-kilometer rod. And you can keep looking and seeing what's happening to the length. And it looks like the length is growing. And the question is, will the length stabilize? Once I get down to the 1 inch, is that going to be enough? Or what's going to keep happening? Is the coastline, is it a fractal dimension? And if so, is it a little bit greater than 1? How much greater? Anybody have any thoughts as to which country might have a really high dimension for its coastline? Very jagged coastline. Norway, right? So, some of those countries with lots of fjords would be a really good one. So I'll skip the rest of the stuff. I want to turn now to some applications of calculus. And this is going to lead to a homework problem that I saw when I was a sophomore, and it's what really pushed me away from being a physics major. I still majored in physics to becoming a mathematician. Just could not believe how well math was able to do this problem. So much of math is about solving equations. The other subjects tell you why we care about the equations we're solving, and then they bring in the mathematicians and we tell you, and this is how you solve them, and this is how you find the answer. So we need ways to solve equations. So if I give you ax plus b equals 0, it's not that hard to get x equals negative b over a. And I'm always going to assume that my leading coefficient is not 0, so this is a real linear equation. If I give you a quadratic, it's not so bad. This is the famous quadratic formula, negative b plus minus square root of b squared minus 4ac over 2a. You should know how to prove that. If you don't, you can use the method of divine inspiration because I gave it to you, and you can just look at x minus the first root times x minus the second root and expand that out, and you'll see it differs from this by a factor of a. Oh, well, of course, I can pull out the factor of a so that it's a monic polynomial. So again, it's one thing to be able to prove something from first principles and just look at it, but a lot of times if you're told what to prove, you've got a great hint. Oh, okay, you want me to show that those are the roots? I'll do the algebra. It turns out that there are formulas for the cubic and the quartic. In the old days, mathematicians could challenge each other. And so things were a little bit different. They would not fight till the death. They would fight either for their position or for pride, things that were really important. And so someone came up with a formula to solve the cubic, and he kept it secret. And this way, if anybody ever challenged him, he would just send, as his response, find the roots of these 10 cubics. And the idea was, well, he has to prove that he can do it. He can give his list of solutions without telling how he got them. And so, of course, the question is, could you sniff out his method if you know the roots? Well, I don't know how carefully he prepared himself. If I ask certain questions, I might be able to start sniffing out what your method is and get an idea of what the general formula is. How many of you have seen the formula for the roots of a cubic? It is unfortunately too late for me to add material for the next exam and say that you are responsible for learning this by Monday. So it's a real shame, but we at least have the final. There is no way you should ever memorize something like this. These are the 3 roots of the cubic. But there's an explicit formula. And what's wonderful about this is it tells you if I vary some of the parameters of my cubic by just a little bit, how do the roots change? And you can see they're not going to change that much if it's a small variation. Now, there are things you could do to make it a little bit simpler. I claim that without loss of generality, you can assume A takes on a certain value. What value should we assume A takes on? 1. We're assuming A is not 0, so let's just divide through by A, and without loss of generality, A equals 1. This is similar to a lot of what we were doing when we were doing the equations of a line, using a vector direction for the slope. Well, can we just say without loss of generality, the x-coordinate is 1, and then the y-coordinate is m? No, because I could actually give you the line that's going vertically upward. So I can't assume that the x-coordinate of the vector is 1. I can assume, however, that unless it's zero, which I have to handle separately, every other case, I can always adjust so that the x-coordinate is equal to 1. All right, it turns out not only can we make A equals 1, but we can replace x with x minus alpha and adjusting so that the coefficient of the x squared term is 0. So with a little bit of algebra, I can make A equals 1, B equals 0. It's still going to be bad, but it's at least a little bit better. I unfortunately don't have space to show you all 4 roots of the quartic on one slide, and this is with decreasing the font size a little bit. So this is one of the 4 roots of the quartic. There is an explicit formula for roots of the quartic. Again, things you should not memorize. There is no explicit formula for degrees 5 and higher. I cannot write down a formula involving just multiplication, addition, subtraction, division, roots, and whatnot that will give you the solutions to a quintic or higher. Now, if the quintic is nice, if I give you x to the 5th minus 1 equals 0, I can solve that. I can write down the roots for that one. But a general quintic, I can't give you the solutions in terms of the coefficients. So we're moving to a new type of mathematics that you might not have seen much in high school. In high school, did you ever get a problem you couldn't solve, or that someone in the room, or the teacher, or someone was unable to solve? Or was every problem solvable? Every problem, here's the integral, here's the derivative, here's the root. Well, in the real world, it's not like that. Most of the time, we can't write down nice closed solutions. What we have to do is we have to try to find ways to approximate. And again, this is an opportunity to review some of the material before the midterm. One of the things on the midterm is the Taylor series, where we take a very complicated function and we start approximating it with more and more terms. And if your x is very small, the hope is that this will be a really good approximation. Okay, and so what we're going to do is we're going to try to find a sequence of terms that will converge to the roots of our polynomial or the roots of our equation. And hopefully it will converge quickly. So here is a partial plot of a function. It's negative near 0, it's positive near 1. And the function is continuous. What can you tell me about this function? What must be true? Yes. Excellent. Why does it have to cross the x-axis? Okay, so what are you appealing to? What result guarantees that it has to cross? You're correct, it has to cross. What result are you using? I'm sorry? We don't necessarily know that it has to be an odd power. We do know that the number of roots, I think, has to be odd here. But I'm saying there's a theorem from calculus that guarantees, it's one of the 3-letter theorems, the intermediate value theorem. So I might have shared this before. The reason transporters were invented in Star Trek is they had a very small budget, and they couldn't afford to build a shuttlecraft for the pilot to bring people down to the planet. And so said, well, let's just push a button, and then all of a sudden people instantaneously go from being on the ship to on the planet, and we don't have to build the shuttle set. So we just need some kind of like wavy. Yeah, we can do wavy. Yeah, we can do wavy. Yes, let's do that. You're not going to have the function discontinuously jump from negative to positive and then continue. So the intermediate value theorem says if you start off at -1 and you end up at 4, you have to cross all the values between. You might cross them many times. You might cross values outside. You might get all the way up to 28. That's not guaranteed, but you will hit every number from -1 to 4. And so since we start off negative and we end positive, this is a way to try to find the root. We know there has to be at least one root between 0 and 1. So we're going to use the method called divide and conquer. So we'll assume f is continuous, assume it's negative at a and positive at b. Then there has to be a root between them. So let's look at the midpoint, a plus b over 2. If it's positive at a plus b over 2, then we know there's a root between a and a plus b over 2. If it's negative there, we know there's a root in the second half of the interval. And if the function happens to be 0 at a plus b over 2, yay, we found it. Okay. Who here has ever read the instructions on a bottle of shampoo? All right, and I've written here, what does the instructions tell you to do? Lather, rinse, and repeat. And that's what you do here. This is shampoo mathematics. We just keep doing this, we keep doing this, we keep doing this, we keep doing this. When lather, rinse, repeat, are you supposed to lather, rinse, and repeat the lather, rinse, or do you keep repeating the whole cycle? If you keep repeating the whole cycle, you never stop. You spend the rest of your life. That's how we do mathematics. We just keep doing, we keep doing, we keep doing, until eventually we think we've done enough that we're happy with the approximation we have, and we say that this is good enough. Okay? Cultural extra credit. If I wanted to show a movie where a key element in the plot involves hair care, anybody know what movie I'm thinking of? Excellent. So email me for cultural extra credit. So let's look at the function x squared minus 3. So x squared minus 3 has 2 roots, square root of 3 and negative square root of 3. The square root of 3 is about 1.73205080756, approximately. So let's see how well divide and conquer does at finding it. So if we start off at 1 and 2, this is not a particularly great initial start. You know, I know 1 squared is 1. I know 2 squared is 4. F of 1 is negative. F of 2 is positive. The root has to be somewhere between 1 and 2. I then look at the midpoint, 1.5. 1.5 squared minus 3 is going to be negative. So I know the root has to be somewhere between 1.5 and 2. I then check 3/4, and I get f of 3/4 is going to be, I'm sorry, f of not 3/4, 1 and 3/4 is going to be positive. So the root is somewhere between 1.5 and 1.75. And so I'm going to do this 10 times. And I get that the root is somewhere between 1.73 and 1.732. And so unfortunately, it's cutting off the bottom of the screen here, although it does have it in the slides. I will write down on the blackboard. It is approximately 1.7320508, and I think it's 0756. So we did 10 iterations of divide and conquer, and we know it's somewhere between 1.730, 1.7324. The actual answer is 1.7320. It's not terrible. We've got approximately 2 or 3 digits right. And let's think about what happens. every time we do a divide and conquer, we decrease by a factor of 2 the size of our interval because we're chopping it in half. So if we were to do this 10 times, we would get 1 over 2 to the 10. Is there anybody here who's thinking of majoring in computer science? Or at least knows a lot of, or can program? Can anybody tell me how many megabytes are in a gigabyte? Not 100. Not 1,000. 1,024. If we actually followed the classical languages to what you should do from mega to giga, it should be a factor of 1,000. But the computer scientists have said, 2 to the 10 is 1,024. Computers love base 2. That's approximately 1,000. So we're going to just use that notation. So sometimes when you're looking at downloads and you're downloading something that's a little bit over a gigabyte, it's interesting watching as it goes from 980 megabytes to it goes over, but then just in terms of what it's writing in terms of the fraction of a gigabyte. So every 10 iterations, my uncertainty becomes 1 over 10 to the 1 over 2 to the 10th or 1 over 1024 of what it was before. So that's essentially gaining 3 decimal digits. So if I wanted, let's say I wanted 9 decimal digits of accuracy, how many times would I have to do this to get 9 decimal digits approximately? So 10 times gave me 3 digits, 30 times. So if you want 9 digits of accuracy, we're going to have to do divide and conquer. Okay. Let's do it another way. And again, this way we can review a little bit of our calculus. We love point slope. If I want to write the equation of a line, y equals y minus y naught equals mx minus x naught. If my line is not vertical, I can, here's my slope vector 1m. I'm just moving over. And the big idea in calculus is that the tangent line locally does a great job of approximating your function. And so f of x, the new location, is approximately where I started, f of x naught, plus my instantaneous speed, f prime of x naught, times the elapsed time, x minus x naught. This is the equation of the tangent line. So I'm just finding the line going through the point x naught, f of x naught, with instantaneous speed or slope, f prime of x naught. And so just as an example, if I give you a cubic 2x cubed minus 3x plus 1, I calculate the derivative, I see what's going on at the point 4, and you can see it's doing a pretty good job. If I zoom in, you see it's doing a really good job of fitting the function over a reasonable interval. And so the hope is that the tangent line does a great job of approximating the function. So what I can do is I have my guess. I'm looking at this point and I flow down the tangent line and I see where do I hit. And that will be my next guess for my root. It's not correct, the root is a little bit, and then I'll play the same game and I'll draw the tangent line there and I'll keep playing. So this is how Newton's method works, is I give you some function, I have some guess xn, I calculate the tangent line at that point, and then I see where does that tangent line hit the x-axis. Well, when it hits the x-axis, the y value will be 0, and my x value will be my next guess, will be my xn plus 1. And so when you do the algebra and you solve, you get xn plus 1 is xn minus fxn over f prime of xn. So we'll talk about that algebra in a little bit. So here is a picture to illustrate what's going on. I start off with my guess x naught. I calculate my tangent line. It hits the axis at x1. Lather, rinse, repeat. I do it again, and I now calculate the tangent line at x1, and I see where it hits, and I'll call that point x2. And I keep playing the game, and the hope is that this will do a great job of approximating where the root is, that it will converge quickly. Which do you think is going to do a better job, divide and conquer or Newton's method? Now, I've shown you the data for divide and conquer. I have not shown you the data for Newton's method. Newton's method, has the word Newton attached to it, right? What does Newton's method use that divide and conquer doesn't use? So divide and conquer, I assumed I have a continuous function. What am I assuming here? My function is continuous and differentiable. So the hope is by using more information about the function, I can do something better. It's not going to be as applicable as divide and conquer. For divide and conquer, I just need my function to be continuous. More functions are continuous than continuous and differentiable. Why? Well, if you're continuous and differentiable, you're clearly continuous. So there's no chance of more functions being continuous and differentiable than just continuous. And there are functions that are continuous but not differentiable. So it's a bigger space that divide and conquer applies to. And because it applies to more things, it turns out it's not as powerful because it has to handle more cases. Newton's method is going to do a lot better. So if I give you the function x squared minus 3, if I use the formula I told you, after the dust settles, you get xn plus 1 is 1/2 xn plus 3 over xn. Let's try to get a sense of, is this reasonable? Can somebody give me, if you were incredibly lucky, what would be the best value of xn for you to get? Why 3? Okay, but that's just a number that's easy to do the algebra. 3 is not the number that we're trying to search for in this problem. What's the number that we would love to get? I'm sorry? Well, 0, it's going to blow up. I'm sorry? Root 3, right? We're searching for the square root of 3. We're searching for root 3. Imagine we were lucky enough to try to do Newton's method at the square root of 3. Then we would get root 3 plus 3 over root 3. What's 3 divided by root 3? That's root 3. So we get 2 root 3 divided by 2 is root 3. So if you start at the root, you stay at the root. Whew, okay, that's good. It would be really bad if Newton's method took a solution that was perfect and moved you away. Let's take something like 100, which is a bad guess. If we take 100, the next number is 1/2 of 100 plus 3 over 100. That's approximately 50. And the next one would be 1/2 50 plus 3 over 50. That's about 25. The next would be 1/2 25 plus 3 over, that's about 12.5. So you can see that if your guess is very bad, it seems to be falling down towards 3. If you start off with 1 over 100, well, because I have 3 divided by xn, that would then crank it up to being very large, and then it would fall down. So you can ask, how quickly will it converge? When will it converge? Will it always converge to the root you want it to? Okay, so again, this is the equation of the tangent line. In the interest of time, I'll just put up all the algebra at once. We said that when it hits the x-axis, y is 0, and my value of x is the next one. When you substitute for what the function is and you do the algebra, at the end of the day, you get xn plus 1. The algebra is not that bad. I strongly urge you, if you are uncomfortable with doing algebra, to just try to do this, not for maybe x squared minus 3, but maybe x cubed minus 3. Come up with the formula for the cube root of a number. All right, let's see how well it works. So again, when the dust settles, you get 1/2 xn plus 3 over xn. Let's see how well it works. Does everyone agree that 2 is not an unbelievably good initial guess for the square root of 3? Yeah. It's not particularly bad. I'm not going to guess the square root of 3 is 1. I'm taking what integer is closest to the square root of 3. All right, well, let's see what would we get for our next one. We would get 1/2 2 plus 3/2, that's 7/4. That's 1.75. Correct answer is 1.732050807. Okay, that's not bad. Let's do the next guess. We put in 7/4, and when the algebra settles, we get 97/56. 1.73214 versus 1.73205. We're off by 0.00009 approximately. That's not bad for 2 iterations. And it's not only that, but it's a rational number. If you do it the next time, you get 18,817 over 10,864, 1.732050810 versus 1.732050876. We have 1, 2, 3, 4, 5, 6, 7. We have 7 digits right now, and we end with 100 rather than 0.76. We're off by 0.00000000024. And that's after just 3 simple iterations. So if you have, okay, good. It's not cutting anything off. So I did 5 iterations. Here's the actual fraction you get. It's not horrible. And if you want to look at how many digits of accuracy I have, you have to go almost to the end of the line before you finally see a difference with 5 iterations. Divide and conquer gives you about 3 decimal digits every 10 iterations. Newton's method doubles the number of decimal digits, essentially, after each iteration. It is far, far superior. This is what just floored me when I saw just how well this works. After 5 iterations, to have this level of accuracy, this is absurd. All right, so let's play a game. I'm going to give you the function x squared minus 1. I know it is not hard to find the roots. The roots are 1 and -1. Let's play Newton's method, and let's see for different values of starting seeds, do we converge to the red root? Do we converge to the blue root? Or do we converge to neither? Does anybody want to give me a conjecture for which converge to red and which converge to blue? Yes. Good. Left of 0 converges to -1, right of 0 converges to 1. What about 0? Right. If you try to put in 0, you have to divide by 0 immediately. And so it's not going to work. So you're absolutely correct. How would you classify these points? You could say that they're the negative points. How would you describe them in terms of the roots? Not imaginary. What do all of these numbers have compared to -1 versus comparing them to 1? Negative sign, but how might you describe it? Geometrically, not decreasing. So look at the picture. If I look at these roots, what's their relationship to -1 versus their relationship to 1? They're closer. That's a really nice property. You seem to converge to the closer root. Wouldn't it be nice if that was always the case? Let's look at x cubed minus 1. Now, what's wonderful about this is I know you all remember your polynomial long division from algebra 2. And so if you look at x cubed minus 1, well, clearly if I put in x equals 1, I get 1 cubed minus, so 1 is a solution. So I do my polynomial long division, I divide by x minus 1. I'm left with x squared plus x plus 1. I use the quadratic formula, and I get my roots, which are sadly cut off. They are -1/2 plus I root 3 over 2, and -1/2 minus I root 3 over 2. So we have, our 3 roots. So we can apply Newton's method to these 3 roots. I'll call them red, blue, and green. Which points do you think converge to the blue root? Which do you think converge to the red root? Which do you think converge to the green root? Anybody want to make a guess or conjecture?
Any point to the right of the y-axis the blue root?
So if I'm all the way over here, you still think I'm going to converge to the blue root? So it's not a bad conjecture, but there should be some kind of symmetry here, right? If what you said is correct, then you would have 50% of the roots, 50% of the roots are converging to blue, and then maybe less than 50% would be going to the other 2.
Can you try and draw like some line?
Like this?
Yeah.
So here is the line of all the points that are equidistant from red and green. Here's the line, all the points equidistant from green and blue. And so if life was nice and simple, what would be your conjecture? Which points would go to red? Which points would go to blue? What would you guess? Yeah, so each section, you go to whichever root is closest. So computers can do the simulations, and this is what you get. So we color each point in the plane based on what it goes to. The answer turns out to be a fractal. This is absurd. Okay, if I'm near the red root, I'm red. If I'm near the green root, I'm green. If I'm near the blue root, I'm blue. That's okay. But now, for some of these points here, I'm definitely closer to the red and the green root than I am to the blue, but I go to the blue. And then you have this incredible sensitivity to initial conditions. I will risk trying to play the YouTube video. So we'll see. Okay, we're going to get a commercial for baking chocolate chips, I think.
Tonight's dinner, it's gonna be great.
All right, so this should be a zoom in of which route we converge to. I'll try to turn off the lights so that it can be seen a little bit. It is a interesting question as to how do you compute stuff like this in a reasonable amount of time. And so you can see this incredible sensitivity to initial condition. You can also see, interestingly, this incredible symmetry. You keep seeing the same thing as you keep zooming in more and more and more. Okay, so this gives us a sense of what a lot of modern mathematics is like. You can start off with a very simple problem, and very quickly, some incredibly advanced stuff can emerge. We're seeing these fractal behaviors that we start off by looking at when we're trying to understand what dimension was. We're seeing that when we're looking at this dynamical system, trying to see which route do we converge to. Stability is extremely important. It would be terrible if you had to know things to such a precision that a small error leads to wildly different behavior. So I'm going to use this mouse as a simulation of a pendulum. Can anybody tell me the equilibrium points for this pendulum? This is an ideal pendulum. I sadly cannot move it higher than this, the way everything is locked down. So when you have a pendulum, where would it be in equilibrium? Where would it be in equilibrium? What position? If I move it a little bit like this and let go, is it going to be in equilibrium? It's going to start to swing. So where would the pendulum be in equilibrium? I'm sorry? Okay, where would that be? If I move it off like a little angle like this, it's going to start to swing. What do you mean by at the origin? What is 0, 0 mean? When it's hanging straight down, if it's hanging straight down and I let go, nothing's going to happen. If this was a rigid rod, there's another equilibrium point. What's the other equilibrium point? Straight up. Now, it's not going to work on this. This is a cheap cord. But if it was a perfectly rigid, straight up would also be in equilibrium. Now, if I move it ever so slightly from that equilibrium point upstairs, what's going to happen? It's going to start to swing wildly. If it's hanging straight down and I move it just a little bit, it's just going to oscillate a very small amount. And so we would say one of the equilibrium points is stable, one of them is unstable. And the unstable one can be very bad because if you change your values by ever so slightly, you get a wildly different answer. One of my former students does a lot of modeling for climate change. And one of the things he's told me is that a lot of the models are extremely sensitive to values of certain parameters. If you change these parameter values by a very small amount, you get wildly different behavior. And so he's not saying climate change happens. He's not saying climate change doesn't happen. He's just saying the models that are being used are very sensitive in certain parameters. How sure are you about those values? Now, if we can tell, look, I only need to be within 10% of this. Okay, that's good. If I need to be within 1 part in 10 to the 10th, that's very different. And do we have things that are this accurate? If you go back to the first day of class, when we talked about adding speeds in special relativity, it looks like speed is additive. If I'm on a train going at 100 miles an hour and I'm jogging at 10 miles an hour, it looks like to somebody on the platform that I'm going at 110. I'm not, but the difference is so small that people didn't notice that for years. It's not till you got to speeds close to the speed of light that you would start to see the difference. All right, so this is a good place to stop the lecture.